Oh.
Alrighty, howdy. Welcome back, guys. Thank you for being flexible with me last week. My exam went well, so life is good. That is a stressor behind me. So we're getting back to our exam week this week. I did release exam 4 grades this morning. When you're looking at them, if you didn't see my announcement, I think it was exam B and D both had some point adjustments to them. Like I think B was added up to 99 and D added up to 106. So if you're calculated by yourself against the answer key, just make sure that you check the corrected points that we allotted for each exam. So they should add up to 100. Say it again. So it should just be however many points is on the answer key that he posted the modules. It should have like the corrected number in the question. So instead of it saying like maybe it was 11 points and now it's 10 points, I just changed that in the answer key so that it only counted it for 10 points and not 11. So we just adjusted them so that they all add up to 100 points rather than 99 or 106. Yes, yep. So the B exam is also the one that has the corrected exam or corrected answer choice. And he showed you in that on how to actually do the correct or how to get to the correct answer. Are there any questions on exam 4 grades or just grades in general?
Are the grades
Yes, so everything should be in Canvas unless you've like emailed me recently about something that you're missing. But your like midterm grade should be reflective of what I had at the time for your lab grade. I think it was only like a maximum of 45 points. And you have 250 points coming from lab. So, right, it's very minimal lab points that were actually graded at the time of midterms that are accounted towards your grade, and then your first 3 exams. Yes.
At the end of it, does he, whenever he does a final curve, or do you put the lab points in there?
Yes. Yep. So your total grade is calculated from your 6 best in-class exams. Right, because you're going to take 7 total. You'll drop your lowest one, and then 150 points from your final. So that's 750 points from class in general, and then you have 250 points from lab. So how we'll calculate your grade is add up all of those points. It'll be something out of 1,000. I'll divide that by 1,000, multiply by 100, and that'll be how many points you have for the exam.
The exam and the lab too.
Yes and no, because it's like a separate grade, but it's just how many points out of 250. Yeah. Yeah. Yes, it'll be based off of how many total grades I have, right? If someone has like 1 exam, then I'm not going to count them. It'll just be based off of who's enrolled and has all the grades necessary for it, except if you're like missing 1 exam, but you have everything else after I dropped your exam, then you're probably still going to be counted. Anything else on grades? Feel free to email me at any point if you have any questions. If you like want to know where you stand in the class. I think Dr. Lindahl tells you the distributions of A's, B's, and C's every time, like the percentages. It's going to be pretty reflective. We might like bump up the A's a little bit towards the end, but we're going to keep that distribution for the rest of the exams. So you can kind of expect that. And he probably told you today that exam 4 was a lot better than the previous 3. So that's very exciting. You're getting better, learning his exams. Anything else? Okay. Anything for me for exam 5 before we go over the homework, because I'm expecting that's what you want to see. Okay. Okay, so one thing I want to point out, because I did get a couple of questions during your exam, always make sure you look at the top of your exam paper. It should have all of your necessary KA, KBs, or any other constants that you might need. If you think that there is a constant that should be on your exam that is not given, please tell me during the exam. But like always your KAs or KBs needed, if they're not what you're solving for in the question and you need it, should be at the front of your exam. So that should always be there. Just make sure you're checking for those in case you don't know. And then just also make sure that you're looking for, maybe sometimes you're given the Ka, but you need the Kb, or you're given like acetic acid instead of the acetate ion. You should know the difference between like your weak acid and your conjugate base. So those are important because they might be almost like hidden, but given to you at the front of your paper. Okay, moving into what you actually care about. Question 1, true, false. The equivalence point of an acid-base titration is when the concentration of acid equals the concentration of base. Is this true or false, and why? False. Why is it false? Yes, for titrations, you're looking at the moles of your acid and the moles of your base. Oh, that's very big. This is very important if you're looking at a like diprotic acid or diprotic base. You want to make sure that your acids or that your moles of the acid and base are always what equal together. And this is important for like your Henderson-Hasselbalch equations, where you have concentrations in your Henderson-Hasselbalch, but you can also use the moles in general. Alrighty, question 2. The solution in the burette of a titration is called the titrant. True or false? True. This is true. Yep. So you will have your titrant is going to be in your burette, right? If you have a flask that you're titrating into, what is that called? Or what is in the flask? That's your titrant. Any questions on the difference? Question 3, in designing a buffer, use the weak acid that has a pKa nearest the desired pH. True or false? Yes, this is true. Why is that true? What does using a pKa around the same pH do for your buffer? Go ahead.
Why doesn't it use like the equation then find the constant?
Yeah, awesome. Right. So whenever we're talking about a buffer solution, we're usually using the Henderson-Hausbach equation. The whole point of a buffer is, for lack of a better word, to buffer your solution. So it means that if you add a little bit more base, there's acid in that buffer solution in order to combat that base that you added. Similarly, if you add more acid, there's base in there in order to combat that as well. So you can adjust, you can titrate something in, you can add a little bit more acid, add a little bit more base, and your pH will stay relatively the same. It allows for like biological systems to behave properly, or in lab, it allows us to keep enzymes or whatever you're using at the correct pH so that it's not like super acidic or super basic, denaturing your protein. Okay, so the whole point of a buffer is to mitigate the change in pH. So you want to use a pKa very similar to the pH that is desired. Any questions on the idea of a buffer? Question 4. Silver chloride will precipitate if 2.34 micromoles of silver nitrate are added to 3.2 micromoles of sodium chloride in 2.3 liter volume solution, or final volume. Why do we say false? Awesome, right? So whenever we're looking at this, if you're not sure if silver chloride is solid or soluble or not, you can always look at your solubility products given at the top. And we see that we do have a KSP for silver chloride. If we're given a KSP, we can solve for Q the same way that we would solve for K in any of the other equilibriums that we're talking about. So if we solve for Q, because we don't know if we're at equilibrium or not, we can say Q would be your Ag plus ion multiplied by your silver chloride ion. Okay. What do we plug into your concentrations here? Do we plug in the 2.34 micromoles? No. What do we have to do? We have to convert it to molarity or a concentration. So we're going to plug this into, the other thing to note is that silver nitrate will dissociate into silver plus and nitrate minus. And sodium chloride will go into Na plus and Cl minus. So those fully dissociate. So whatever concentration of that starting salt you have will become the concentration of the ion of interest. So this turns into 2.34 times 10 to negative 6 divided by 2.3. Multiplied by 3.02 times 10 to negative 6 divided by 2.3. Questions so far? Here, Q, what does Q equal? Okay, right, we get something to the negative 12. KSP from our top is 1.8 times 10 to the negative 10. Negative 12 is going to be smaller than K. So Q is less than K. So which way do we go, towards products or reactants? We go towards products. Okay, so nothing will precipitate because we need more things in solution. So your solid will actually just stay dissolved. So you can add more to the solution.
I noticed that what's talking about
Mhm.
Tell what our perspective is of the precipitate stuff. Basically, would you ever ask a question? Like what precipitate is?
He could, right? He could say, right, he could do a multi-part question, right, and say, pick the salt that's formed, does it precipitate, right? So you could say, okay, he could give you one where it's just silver nitrate again, right? That's just the thing that forms. And you could say like, no, it doesn't precipitate. So you should be able to remember your solubility chart and like what is soluble. So right, your nitrates are always going to be soluble. Anything in the first column will always be soluble. Everything in your halogens will always be soluble. So if you know those rules, then you can decide what's going to be your precipitate. You also have your KSPs given to you. So if you're looking at something, you're like, okay, these two ions are here, it's in my KSP, you can kind of assume that that one will also be a precipitate. Does that help answer your question? Yeah. Yeah. I guess potentially. I think the biggest question that he could ask is, this is mixed with this, does it precipitate form? Right. And then you have to know, okay, these two will form our precipitate. And then using those concentration, using those solubilities, what would be my cue here? Any other questions on solubility? The other thing to note is that the X in solubility or in your solubility product is considered the solubility of that ion. So the solubility of that ion is what you solve for if you are given KSP. And if you're given solubility, then you know what X is. Alrighty. Question 5. A 1 molar solution of a weak acid HA with pKa 7 would be an effective buffer against a perturbation against caused by adding 0.1 molar of HCl. Words are hard. True or false? Anyone have an idea? True or false? Yes. Why is it false? Yep, we're adding a strong acid. And so your strong acid is going to be in the pH of like 0 to negative even for hydrochloric acid. So we want a pKa that's closer to that lower end of the acidic range. So something that's at neutral or 7 is not going to be able to combat that very acidic stuff that you're adding to it well. So we have a bad buffer system here. We would want a pKa closer to probably 1. All right, something very far on that acidic range. Go ahead.
So I have a question like with like finding like the pKa. So like if you're, it said like you're adding the HCl in, so you're wanting to find a pKa that's close to the HCl, but what about the stuff that you're adding it into? Does that make sense? The question I'm asking?
Yeah, so the pKa is referring to what you're adding into.
Okay.
So when you have something that's 7, that means it's going to buffer something that when you add to it is around that 6, 7, 8 range.
So like it's about finding like the ideal like buffer. It's about what can buffer what you're adding.
Yes.
Not
Yes.
what you're adding it to.
Yes.
Okay,
Yep. Because the buffer itself is going to be some acid, some base around that pKa that you're looking at. So you're going to be adding that stuff to it. And the idea of a buffer is how can that buffer mitigate what you're adding?
Okay. Got it. That makes sense.
Does that make sense? Okay, go ahead. Yep, absolutely. So, yep, if we had something in like the micromolar range of HCl, we could find what the concentration of H plus would be in that case and what the pH of that would be. If the pH of that is very close to your pKa value, then you probably are going to be okay. But since this is a pretty high concentration of a strong acid, the pH will be just too low, getting you out of that buffer range. Good question. Go ahead.
So this one's false because the pKa of the HCl would be super low.
The pH of this specific concentration of HCl would be super low, right? If we found the pH here, it would be the negative log of 0.1. And what is the negative log of 0.1? I don't know. Probably should at this point. Yeah, this is 1. So since 1 is way less than 7, it's going to be out of the buffer range for the buffer that we're using. And so it's not going to be able to reduce the effects of the acid being
But
added.
if it was like 5,
Yep, if it was 5, we would get a little bit closer. Your buffer range is plus or minus 1. So since your pKa is 7, you can go anywhere from 6 to 8. So if we had something that was like 1 times 10 to the negative, we'll say 8 molar, what would this be? Yeah, this is 8. This might have a better chance of being buffered by it. It's at that top end, but so it might mitigate a little bit, but it's still going to see the effects pretty bad.
want it as strong as the other.
Yeah, you want it like as in between that buffer range as much as possible. Yep. Yes. Yes. Yep. Yeah, absolutely too. Go ahead.
Is the buffer range measured in pH or pKa?
pH. Yep. Because you want a pH similar to your pKa, so you can look at plus or minus 1 pH that it can buffer. All good questions. Go ahead. No, it's more of the concentration that you're adding. Yes. Yeah, so your range is plus or minus 1. So if you have a pKa of 7 and the thing that you're adding is 5, right, that's going to be out of your range because you're 2 pHs away. But if you have something that's 6.5 that you're adding, then it could be okay. It could be buffered. Any other questions on buffers in general? Great questions. Okay. Question 6. The Henderson-Hasselbalch equation cannot be used to calculate pH at the equivalence point in an acid-base titration. True or false? True. Because what happens when we use the Henderson-Hasselbalch? Like what goes awry in this case? Yes, right. So here, the equivalence point means that you're using up, you have the same concentration of moles, or you have the same moles of acid and base. So your concentration of these are the same, which means that you are using up all of your moles. So in your pH is equal to pKa plus the log of acid over base. You are now dividing by 0 in your log function, and that screws up your whole equation. So here you actually have to use an ice table in order to solve the pH at this point. Go ahead. And yes, and that's at the half equivalence point, not the equivalence point.
So anything beyond the equivalence point, including the equivalence point.
Right. Yep. Equivalence point and beyond, you have to use just regular ice tables. Anything in between, you can use the Henderson-Hasselbalch. Anything else? Yes. Yep. So if we were to look at right, we're looking at this. Your moles are equal to each other. I think there is some example. Hold on. Right, so you have equal numbers of moles of acid and base. So sorry, if you don't write it like this. No, maybe you do. I'm getting all confused. Right. I'm sorry, I'm doing equilibrium. This is not even the correct question. You will have HA and you have OH minus. If you have a weak acid and a strong base. This comes together to form H2O and A minus. So in your buffer solution, when you're using the Henderson-Hausbach equation, you're using this one and this one. In your titration at the equivalence point, you could have 0.5 of this and 0.5 of this, for example. And these are in moles, not molar. That means that your 0.5 moles of acid, 0.5 moles of base will react completely to form 0.5 moles of your acid, or of your conjugate base, excuse me. Okay, so you end up having 0 of your acid and all of your conjugate base. Yes.
And this will be why you can't be off equivalent.
Yep, so, yep, beyond equivalence point, using that same equation, where you have HA and OH minus, goes to H2O and A minus. Beyond equivalence point, you're now adding more base than acid in this case. Okay, so you can have 0.5 of this, and you can have 0.6 of this. Your limiting reagent now becomes your acid. So you'll change this so it's 0.5. And you have +5 here. I'm gonna move this. And this will be plus 0.500. So at equilibrium, you now have 0.1 of your acid, or of your OH minus, and 0.5 of your base, of your conjugate base. So now you can just find the pH from your POH, because now you have so much more excess of that OH minus ion.
So we're gonna. And this will still why we can't.
Yep. So at equilibrium now, right, because this is ice, you now have 0 of your HA. So if you plug this into the Henderson-Hausbach equation, you get plus the log of 0.5 over 0. And you can't have that 0 because that ends up being undefined. Yep. Any other questions? Dr. Lindahl, if you haven't looked at his PowerPoint, does go through a lot of titrations by 10 mils at a time in his notes. And he does a good job of explaining that too if you have more questions on like when to use it, when not to use it. Alrighty. Question 7. Consider a titration of 200 mils of 0.045 molar formic acid with 0.145 molar sodium hydroxide as the titrant. Using graph paper, generate a plot of pH versus volume of the titrant added in increments of 5 mils. Find the pH at the beginning of the titration, the half equivalence point, and the equivalence point. Hey, we're not gonna graph this. We can give you in terms of like 5 mils. We can discuss the pH before, at the middle, and after. And then we can draw a general curve of what this would look like. Does that sound okay? I don't think so. Because this requires you to draw. And like, right, I have to grade it, and we're doing multiple choice. So he might have you like draw it and pick a graph. Yeah. So you just need to know what your general shapes of graphs looks like. But if you can produce one yourself, you can identify one. Alrighty, so for part A, we're looking for at the beginning of the titration, what is your pH? What do we do in order to find this? First of all, before you answer that question, what type of titration do we have? What kind of acid are we using? We have a weak acid and a strong base. So before we even begin, if your sodium hydroxide is your titrant, should our pH at the beginning be acidic or basic? It should be acidic, right? So we're expecting acidic pH. Okay, so at the beginning, we just have this weak acid. How do we solve for pH of just a weak acid? Yeah, we can use Ka. It does not matter what formic acid's formula is. If you have a weak acid, you can always write Ha will break down into H plus and A minus. Right, we're going to do an ice table. We're going to do an ice table where we're starting off with 0.045 molar of our formic acid. Do we have anything to start with, H plus or A minus? No. What's our change going to be? So at equilibrium, we have 0.045 minus X, X, and X. Go ahead.
Why don't you like consider the like?
Yep, so right now we don't need to worry about that. Right now we just have 200 mils, and that whole 200 mils is going to be this concentration of 0.45. So we're not worried about the moles yet because we just have our acetic or our formic acid in solution. And usual Ka weak acid equilibrium, you work in molarity and not moles. Yep. At the end of the day, we want to find pH, and that's concentration, which is in molarity. Okay. At the top of the page, we're given Ka, and it is 1.78 times 10 to the negative 4. Can we use the assumption when we're solving Ka here? I don't have a confident answer. What do you think? Yes. Yep. What are you thinking? Yes or no for assumption? It's kind of close. To be safe, I wouldn't. If you're going to use the assumption, you can always check to see if your change is less than 5%. I did both, so you don't have to. If you use the assumption, it's more than 5%. It's actually like 6.7. So to be safe, I would use the quadratic formula. Whenever you're looking at it, that's kind of close. Just take the extra time, use the quadratic formula, you'll get the more correct answer. So in this case, Ka, which is 1.78 times 10 to negative 4, will be equal to X squared over 0.045 minus X. I pulled my notes up, so I don't have to do this again. We can cross multiply, distribute, and rearrange, which I'm all going to do in one step, to get to X squared plus 1.78 times 10 to the minus 4 times X minus 0. How many zeros is that? 1, 2, 3, 4. 1, 2, 3, 4, 5, 0, 8, 1 equal to 0. And we got this from cross multiplying your denominator on the right times your Ka value, distributing those values, making it equal to 0, where X squared is positive. You can plug this into the quadratic formula, which I will not show unless you need it, but X will be equal to 0.00274. And what does that equal in our question? This is equal to H plus. And it's specifically the concentration of H plus. So how do we solve pH at the beginning? Yep, we can just take pH is equal to the negative log. And what do we get for pH? Does this match what we predicted our pH to be? Yes, it does. Yep. Questions on how we find the pH at the beginning? Coolio. Okay. Question B. We want to know the pH at the half equivalence point. What do we know about the pH at the half equivalence point? Yes, pH will be equal to pKa due to the Henderson-Hasselbalch equation. Right, and this is pH is equal to pKa plus the log of your concentration of base over your concentration of acid. At your half equivalence point, the concentration of base and acid are the same. So this turns into the log of 1, which makes pH equal to pKa. How do we solve for pH then? Yep, so now we can take the negative log of the pKa, or negative log of Ka, excuse me, that would be the pKa. And we know that from the top of our paper and what we just used in question A. And what do we get for pH here? 3.75. So we expect it to be a little bit more basic, right, than what we started off with, but should still be relatively close to our starting pH. Yes, at half equivalence, your concentrations of base and acid are the same in terms of conjugate acid, conjugate base. At the equivalence point ratio, your moles of acid and base are the same. There's like, you can do the, there's like the second equivalence point that's in a diprotic acid. Is there another question? Okay. Any questions on part B? Yep. Your concentrations of your acid and conjugate base are the same. So that's why A minus over HA can cancel out to 1 because your concentrations of both will be the same. Okay, and then question part C, and this is where solving at the equivalence point, you can kind of see what your things will equal. Go ahead.
Is that the concentration?
Mhm.
I thought we were working.
So for your, yes, everything for the Henderson-Hasselbalch you can really either use in moles or concentrations because your volumes will be the same during that buffering region. When you come to this equivalence point, you need to look at moles. So half equivalence, you can look at concentrations. Equivalence, you have to look at moles. And you'll see that in part C here. Okay, so part C, I lost my question. We want to know the equivalence point, pH. Again, the important thing to remember about our equivalence point is that our moles of acid and base that we're adding are the same. So if we have a weak acid and strong base, what do we expect our pH to be? we expect it to be basic. So we're expecting a basic pH, right? Our strong base will overcome the weak acid. We then need to look at our moles of our acid and base that we have. We are starting off with 200 mils of 0.045 molar formic acid. How many moles of formic acid do we have then? Total moles. We're going to take 0.045 moles over liter, right? Because that's molarity, times 0.2 liters, because that is 200 milliliters in liters. And we end up with 0.009 moles. Which means we also have 0.009 moles of the sodium hydroxide that we added. So if we were to write out a reaction, we would have your weak acid and your strong base now form water and your conjugate base. We are starting off with 0.009 of both. They're equal. They're like this, considered both the limiting reactant. All of your reactants will be used to form your products. So all of this turns into 0.009 moles of your conjugate base. We now form a new equilibrium where we have A- and H2O, right? You can flip this, where you have 0.009. You don't care about your water. Will now form some conjugate acid and some OH minus, right? Because that A- will take that hydrogen from your water. Go ahead.
When you flip, you have to change it.
Yes, we're going to do that in a second. Yep. Someone say, why did we flip? Yep. So you don't have to flip. But if you're looking at this in terms of an equilibrium, right, you now have all products and no reactants. So you could solve for Q and you would get Q is greater than K. So it would shift towards reactants. So instead of looking at it right to left, you just flip it so that it's left to right. Yeah. Go ahead. Because we're at the equivalence point. So your equivalence point, you know that your base added and your acid will be the same molars, or will be the same moles. Okay, so we're starting off with 0.009, but we are now in an ice table situation, which means we have to move into concentrations and we can't just use moles. So how do we get to concentration from here? We have to divide by our total volume that we have. How do we find total volume that we need? Perfect. Yep. So we know that we have 200 mils of formic acid. We know that we need 0.009 moles of our sodium hydroxide. We have 0.145 molar. So this is moles over liters. If we multiply this by X, that'll give us how many liters of our sodium hydroxide we need to equal 0.009. Okay, so we can say X would be equal to 0.062 liters. We can add that to our 200 milliliters. So we get total volume is 0.2 plus 0.062. So we get 0.262 as our final volume in liters. So we can divide 0.009 divided by 0.6262. And we get 0.034 molar. We could then use that 0.034 molar and plug that into our concentration of our conjugate base that we're starting with. Yep, so we know that at the equivalence point, our moles need to be equal. We don't know how much volume we need to add in order to get to that equivalence point, but we know our starting concentration of our, or we know the concentration of our sodium hydroxide, and we know how many moles we need to get to. So since molarity is moles over liters, and we know how many moles we need, we can divide by the molarity to get just liters. And that would be how much you need to get to 0.9 moles. So that would be how many you need in order to reach the equivalence point. Yes, yep. You're just doing it backwards. Questions? Did I lose anyone in the math that just happened? Okay. Now that we have concentration, we're just going to solve this like an ice table. Right, we just said that we have 0 because all of our HA gets used up to form our products. So we have 0 of HA and we have 0 of OH minus. Our change is just minus X plus X and plus X. And so at equilibrium, we have 0.034 minus X, X, and X. How do we solve for pH from here? Are we given pH or POH? We can easily solve for POH. So if we're solving for POH, what K do we need? We need KB. Do we have KB? No. Can we solve for KB? Yes. Yep. So we can say that KW is equal to KA times KB. Doesn't look like a B. We know KA from our previous two parts that we solved, and we know KW because that is a constant. So KB will be equal to 1 times 10 to the negative 14 divided by 1.78 times 10 to the negative 4. So KB will be equal to, what's this here? 5.62 times 10 to the negative 11. We can then use KB to solve for X. Can we use the assumption here? Yes, yes. Negative 10 is very small. We can ignore that one. So we have KB. We'll have X squared over 0.034. And we get X equal to 1.38 times 10 negative 6. Yeah, so the other assumption would be like if you had some sort of concentration of OH minus or HA still there, then you would be, right, your change is still plus X. But again, that change is going to be so small you can leave it out. Yep. Yep.
Could you have used the KA that was given, the 1.78? We were there with the extra 1.4.
I don't think so. The only way you could use KA is if instead of flipping your equation, you did the reverse. So you see how we have HA plus OH goes to H2O and A minus? That's going to be your acid dissociation. So you could use it there. Because we're doing, actually, it's not technically your acid dissociation for the HA because we don't have water that we're reacting it. We're reacting it with OH minus. So even the KA there probably would give you a little bit screwed up answer. And probably pretty similar, but it'll be a little bit different. So the best bet is to just use your KB and then solve from there. Yeah. Good question though. Okay, so now that we have X, what does this correlate to in our problem? This is OH minus, so we can find that POH is equal to the negative log of this. And we get 5.86. And how do we find pH? Does this match the assumption that we thought at the beginning? Yep, we expected a basic pH. This is in that basic range, so we're good. Yes.
One thing I don't understand is how, or with the low volume,
Mhm.
so we know the amount of volume we have for formic acid, but we don't know how much we have for the other one.
Mhm.
Since we know that the moles equal each other, why do we multiply by K or by X?
Yep, so in the same way that we, right here, the 0.045 moles times liters times 0.2, right? We used our concentration and our liters in order to find the number of moles.
Okay.
So now we're using our concentration and our moles to find liters because we know what the concentration is and we know how many moles we need to get to.
So it was 0.145 times X equals
Point.
0.0. Oh, okay.
Yes, yep. Yep, go ahead. Because at equivalence point, we move into ice tables. And when we were talking about ice tables, we're talking about Ka or Kb. And those are the acid or base dissociation. And those are all in terms of concentrations. So you have to use your concentrations in order to solve for that. If you do use moles here, you'll get a slightly, in this case, you'll get a slightly lower pH. It's still in that basic range, but it is slightly lower than what it actually is. Yes.
So I don't know for A's, the HA goes to H plus and then
Yep. So that just comes down to what is happening in a titration, right? So in a titration, I ran out of space, but in a titration, we know that we have our, right, we have our little beaker and this has acid. And then we have our burette and this has your NaOH. We know that sodium hydroxide will completely dissociate. So in that burette, you do have Na plus and you have OH minus. We know that sodium does not affect our pH of anything, right? It's just a spectator ion. So you can just assume that only OH minus is being added into your solution. So the reaction that's happening is your acid and your OH minus reacting together. So if we look at like partners or just an acid in general, right? An acid will give up its proton. So this will come to here. So we know that H2O and A minus will be left over. Okay. So that's what's happening in terms of like your, once the titration starts happening. If we are just looking at the acid in general. We know that a weak acid will always have some sort of dissociation, right? It won't completely dissolve, but some of it does dissolve. And that's going back to like last exam, we were just looking at Ka or Kb. And that's where we don't have any hydroxide for that weak acid to interact with. So it's just the dissociation that we care about, producing those H+ ions. Does that help?
Yeah.
Okay, go ahead.
So if he states in question that it's titration,
Mm.
about that, the generalized form.
Yes.
What's gonna be happening.
Yep.
Whenever, base gives your acid.
Yes.
this
Yep.
reaction.
Is this here. Yep, it'll follow the same format. If you have a weak base being titrated with a weak acid or with a strong acid, you will just have very similar equations, but like the base form of it. So, right, instead of it being HA in solution, you have your A- that will, right, you always have that water component in there. It'll form the HA and OH-. So that's what you're going to use prior to the titration starting. Once the titration starts, so like once we get to B and everything, it'll always happen where you'll have your A-. This time you'll have some sort of strong acid, which will produce a anion that will be a spectator ion and an H+. So you have H+, and this just forms your HA. Okay. And then that works the same way. Go ahead.
It's like, I haven't tired of drug target, but it's a small statement. But tell us more about what's going after.
Yeah, so I guess to wrap up this question, right, we need to draw a curve, and there's a curve right underneath this too. But we know that we're going to start off if we just have 1, 2, 3, 4, 5, 6. Right, this will be 2. We know that we said that we started off about 2.5. So it'll be probably about like here. We know that our half equivalence point is at 3.75. If I remember correctly. Yeah, 3.75. Right, which is probably about here. And then we know that our final, our equivalence point, in terms of the titration, is about 8. So that'll probably be about here. Based off of, right, how many milliliters we're adding, we know that this is going to be 62 mils. Your half equivalence point is going to be around that 30 mark. So you could draw a curve where you have a slightly shallow curve that then turns into a big curve. Okay, so if you're given a snippet, right, if you just zoom in on this portion here, right, your curve is now going to look like this, right? And if you have a very shallow curve, you're probably in some portion of the buffering range. If you're at this portion here, your curve is going to look like this. And at that point, you're in your equivalence point range. He would most likely, if he's trying to identify a graph, give you the full thing. And then if he just gives you random concentrations and random volumes, solve for your moles and see what happens, right? Do you have more acid? Do you have more base? Do you have equal amounts? And then you can tell if you're prior, before, or during. Sorry, I'm getting a FaceTime. Alrighty. Sorry, my Zoom quit. Did I not share my screen? Okay, there we go. Okay, back in business. Any questions on 7? Yes. Yep. So if you have a strong acid and strong base, you no longer have the like blue portion that I boxed. You don't have this like buffering range that you're talking about. If you have just a strong acid and a strong base, if your strong acid is your titrant and your strong base is your titrand, what this is 0 and this is 14. Where are we going to start our curve? Yep, probably around 14. And we're going to end up in the acidic range, but we're no longer going to have this buffering region. So you'll just have a decline and then something like that. What will be the pH of your equivalence point for strong acid or strong base? It'll be 7. Does that help with the difference between the curves there? Yep. And then if you had any sort of strong acid or strong component and weak component, you'll have a buffering range. Any other questions on 7? Okay. Okay, so for question 8, which of the following statements regarding the pH titration involving a strong monoprotic acid and a weak monoprotic base shown below are correct? Does anyone have an idea for A, B, for like what letter choice this is going to be? Is there any? Okay, so then I'll ask another question. Out of 1, 2, and 3 for your statements given, does anyone know of one that is definitely true? 2 is definitely true. Right, if we're looking at A, point A, we can extend this line over here. It's just a little bit above that 9 range, so that pKa is probably around that 9.4. At your half equivalence point, your pH will be equal to your pKa. So we know that your pKa is probably around that 9.4 range. Additionally, we know that the titrand is the weak base because we're starting in that basic range, and your pH probe is always going to be in your titrand. What else is true? 3? Yeah, 3 is definitely true. So in order for 3 to be true, this also means that 1 has to be true. So I do think his answer key is wrong. That's posted. I think he was supposed to highlight A. I don't know if anyone asked him about that. Okay, so yes, it should be A. Right, so it's kind of a workaround of how you do this. If we are assuming that A is true, if we were to solve for the volume needed to reach the equivalent point, we know that we have 100 mils of weak base at 0.025 molar. To find how many moles we have, we would say that we have 0.025 moles over liter times 0.1 liter. So you end up with 0.0025 moles of weak base. If we want to find how many milliliters are needed to reach the equivalence point, just like how we needed to find the total volume, like for the part C of the last question, we're going to take our 0.01, or sorry, not 0.01, 0.1 moles over liter of our strong acid times X to get how many milliliters are needed, equal to the same number of moles as our weak base. If we solve for X here, or if we solve for concentration, we know that X will be equal to 0.025. I'm just gonna have too many points. Liters, which then results in 25 milliliters. So if that B line, right, is pointing down to 25 mils at that steep point of our titration curve, we know that this will be the equivalence point when we've added 25 mils. And we just proved to ourselves, assuming A is correct, that C is, or assuming that 1 is correct, that 3 is correct. So in this case, all answer choices are correct. Yes, you probably could. Yeah. I tend to look at B and be like, oh, equivalence point, and then I can solve for that first before using the Henderson-Hausbach equation. Because in this method, there's no logs. But yeah, there's always like going to be two ways for acids and bases that you can usually solve for something. Yep. Any questions on why A is the correct answer choice? Cool. Okay. Question 9. A 25 ml solution of 0.1 molar, I believe that's acetic acid, is titrated with 0.2 molar sodium hydroxide solution. What is the pH after the 5 mils of the base was added? How are we going to go about doing this problem? Yep. So we're in a titration. We have to write out our titration equation. So we know that this, I'm just going to call a HA. It is not one of the 6 strong acids I know, so I know it must be a weak acid. And so we know that HA and sodium hydroxide is what's being titrated with, will just be OH minus. Will form water and A minus. Yep. What do we do next? Yep, we need to know how many moles of each we have through our like pseudo ice table. So how many moles of our weak acid do we have, and how do we solve for that? Yep, we can take our volume and our concentration, and we know that we have 0.1 moles over liters times 0.025 liters. Getting so many things in there. And we end up with 0.0025 moles of weak acid. How do we find our moles of hydroxide here? Same thing, right? We know that we have 0.200 moles over liter times 0.005. Let me go to this.
Wait, why are you
Because we have only added 5 mils of the base. Yep. So we end up with 0.001 moles. Which one here is our limiting reagent? The OH minus. So all of our OH will be used up to form our acid, or to form our conjugate base. So after we change, we end up having 0.00 0.150 and 0.001 moles of our strong weak acid and conjugate base respectively. What do we do now? And what do you mean?
Like, you're saying that 0.015 and put that into.
Yep, so we could say that what did I do here? Yeah, so we could say that we have an equilibrium where we have HA and A minus. Wait, hold on. No, we don't. We don't need to do any of that. We have a weak acid with a strong base. So what equation can we use? We can use the Henderson-Hasselbalch equation. We know that pH is equal to pKa plus the log of acid over, or of base over acid, excuse me.
How is it?
So we don't need to flip it because we are not working with a equivalence point. We're working before the equivalence point. And before the equivalence point, we can just directly use the Henderson-Hasselbalch equation because you will have some acid, some base in solution. Because at the equivalence point, you're going to form all of your conjugate base, and then that turns into a Ka equation. Or Kb equation.
How would we know that?
If you're at the equivalence point, is if you solve for, right, how we solved for the moles of your acid and base, if those were equal, then you would know that you're at the equivalence point. Any questions so far about, yeah.
How do you know if you're beyond?
So if you're beyond the equivalence point, then you would have more hydroxide than weak acid. So you would have some of your OH minus ions still left over after you did your math to subtract out and form your conjugate base. Yep. Yep, absolutely. Absolutely. Okay, do we know the pKa of our CH3COO minus COO8? Acetic acid here. Going to be 1.8 times 10 to the -5. So we can say pH will be equal to negative log of 1.80 times 10 to the -5 plus the log of, do we need to change to concentrations here for our Henderson-Hasselbalch? We don't, you should, because it's concentration, but you don't have to. In this case, since it's a titration, your volumes of both of the final volume will be the same for both of them. So you're just going to divide by 30 both times, and then that'll eventually cancel out because you're dividing. So you can just directly use your moles here. We can have 0.001 over 0.0015. And we get pH equal to 4.56, about 4.56. I want to say not never, but as long as it's a titration and your volume, your final volume is the same, or you would be dividing by the same final volume, then no, you don't have to change it. Yes. No, nope. I used 25 mils for your strong acid, for your weak acid, because that's how much you have in solution. So that's how many total moles you have. Then I used 5 for the sodium hydroxide because that's all that you're adding. So that's the the total number of moles you're adding is just in that 5 liters of the 0.2 molar. 5 milliliters of 0.2 molar, yes.
Why, why are you converting this to PKA?
Because we are given the Ka here. So in order to find pKa, you just have to do negative log. Yep. You divide by your total volume. So you have 25 from your titrant, and then 5 that you're adding. So what's the total volume? 30. Yep. So you divide by 30. What other questions? Yep.
So why, I understand why we don't have to find concentration for the oxygen blocks or whatever.
Mhm.
How are the, like, how is it the same volume that it's putting in? Because 125 and 112.
So we are looking at now total volume when we're looking at the concentration.
Oh, okay.
Because, yep, so it would be 30 total. So you're just taking, right, 0.001 divided by 30, and then 0.0015 divided by 30, and then dividing that again. So this, it would just cancel out.
If we were to do this flipping thing.
I believe so. It's just more math and more room for error. If you're before the equivalence point, I would suggest just always using the Henderson-Hausbach equation.
So for any, when would you have to convert it to concentration for that?
If you're trying to find, it would just be in a situation where it like wouldn't be a titration, which I don't think would ever be the case. But if for some reason, like your acid and base are different volumes, then you would have to convert it to concentration. But I don't think you're going to come into contact with a situation that'll happen like that. What other questions? Okay. People are still with me? Still alive? I know it's very riveting information. Okay. Next question. Question 10. 25 mils of a 0.0268 molar solution of an unknown monoprotic acid was titrated with this concentration of sodium hydroxide. After 10 mils of the base was added, the pH was 5.87. What is the Ka of the acid? Is this similar or different to the one we just solved? It's very, very similar, right? The same setup is going to happen where we need to know how many moles of each acid and base that we have to begin with. So again, we have a weak acid and a strong base reacting to form H2O and A minus. We first need to solve for the moles of acid and moles of base that we have in solution. So we have 0.0268 moles over liters times 0.025 liters. So we get 0.00067 moles of acid. And then we have 0.0633 moles over liter times 0.01. Right, and then we have 0.00063. Sorry, I missed a zero. So how many or how much or which one is our limiting reagent? OH is our limiting reagent, so we'll have we have this many moles at equilibrium. Questions so far? Okay, we can then use this to plug in to our Henderson-Hasselbalch equation. Again, we do not need to convert this to concentration. We can just keep it as moles. So pH will be pKa plus the log of base over acid. We know that pH was 5.87. We don't know pKa. And we know our log of our base is 0.000633. Sorry, my numbers are getting small. And 0.000037. Once we get to the pKa, this is 4.64. So the Ka is equal to the 10 to the negative 4.64, which ends up being A. Yep. I don't think he would ask you a question on a diprotic acid. I think you just need to know what that looks like and what it means and be able to identify, things on it's in the PowerPoint, definitely. And I think he even says, like, we won't do calculations on this, just know it. In terms of like a titration, so it's right, it's multiple equivalence points. So you just have to know where you are, right? So here is HH, here is equivalence. Here, here is another HH with pKa 2. And then here is another equivalence point. So it's like Henderson-Hasselbalch, ice table, Henderson-Hasselbalch, ice table. Questions on 10? Okay, I'm gonna skip the challenge question, finish the homework, and then if you would like to stay for the challenge question, I'll come back to it afterwards. But I do not think the challenge question will be asked on the test. If there is something like that, I apologize. I just don't think that that would be enough time for you to like have this full exam and also a challenge question. But I will still go over it just in case. I don't know what the exam looks like, so I don't know if it's on there or not. But if you can do the challenge question, you can conceptually think about what the challenge question is telling you. You should be fine for this exam. Okay. No. Okay. Okay. Question 12. So now for question 12 and 13, I think we move into the KSP, right? Yeah, we move into more KSP questions. So for question 12, we have a certain volume of a certain concentration of potassium sulfate is mixed with certain volume and a certain concentration of strontium nitrate. How many moles of the solid strontium sulfate will precipitate? So we know here that your your precipitate forming is that strontium sulfate. So if you were to write a KSP equation for this, we would have strontium SO4 equilibrium to strontium 2 plus and sulfate 2 minus. The whole point of this question is to ask how many moles of solid strontium sulfate will precipitate. So we need to know how many moles what's our concentration of ions in solution to see if Q is greater than K, and it will push us back towards our reactants. How do we find how many ions are in solution? Yep, it's X, and where does that come from? Yep, it would be the equilibrium. But do we know concentrations of ions to begin with? Yes, we do, right? We have potassium sulfate and we have strontium nitrate. Those are, right, with potassium, that's a column 1, and then your nitrate will always be soluble. So, right, anything in column 1 and anything that's a nitrate will always dissolve. These will completely dissociate into solution, which means that any concentration of those salts you have will turn into concentration of your ions in solution. So if we're looking at K2SO4, we have 0.00080 moles over liters times 6.5 liters. And this gets us to 0.0052 moles of K2SO4. What is our ratio of K2SO4 to SO4 minus? Or SO4 2 minus, excuse me. Close. It's 1 to 1, right? Because if you were to write out this dissociation, this would be K2SO4 goes to 2K plus and SO4 2 minus. So we have 1 to 1 in terms of salt to ion. Let's just solve for moles so far. We then have our strontium nitrate. We have 0.350 liters times 0.0025 moles over liters. And we end up with 0.000875 moles of strontium nitrate. What's our ratio of strontium nitrate to strontium? Also 1 to 1. Huh? Yep, absolutely. In that case, you would just multiply your number of moles by 2. Yep. Yes, right, because we just solved for concentration of strontium nitrate, but in solution, right, if strontium had 2 ions, then it would be twice that number of moles that are produced. In KSP, do we work in moles or molarity? Molarity, yep, because we always have concentration of ions. So we need to solve for concentration from these moles. What is our volume that we have to use? Total volume. What is our total volume? Yep, it's going to be 6.5 plus 0.350, which is 6.85 liters. All right, so you can divide this by 6.85 and this by 6.85. And then we can plug that into Q. And we can say that's 0.123759 times 0.123128, which is your sulfate ion and your strontium ion. And we get that Q is equal to 9.7 times 10 to the -8. Where do we find KSP for strontium sulfate? At the top. Strontium sulfate is here, and it's 2.8 times 10 to the -7. So is Q less than K or greater than K? Q is less than K. So which way do we proceed with our reaction? To the right, towards products. So what do we form more of, ions or precipitate? We form more ions. So how much precipitates? 0. Yep.
Wait, but let's say it's not that, you would have to do the whole.
Yeah, you would have to find like solubility, KSP, use KSP to find solubility and then subtract out your concentrations.
Shouldn't we like do what you just said instead of the Q, because what if it's the other way around and we have
So for this one, we don't have to do it because our Q is less than K. So since there's not enough ions in solution to reach equilibrium, we're going to actually produce.
But I'm saying like on a test.
Yep.
Shouldn't we do the other way? Because if we do this and it ends up not being less than Q, then we have to do all the other steps. Like for time wise.
Yes, I guess so. Time wise, probably.
Because if that ended up being greater than whatever, then you have to find your X, then you have to.
Yep. Which I don't think from here would take too many steps because we've already found all of your moles and concentrations and everything. So like either way, it does set you up to be successful. If Q ends up being greater than K, then you should always solve for Q anyways. Like at some point you're going to have to solve for Q. So then you just have to set up your ice table afterwards if it ends up being greater than K. Yeah. You could also, yeah, absolutely. You could also look at it that way, right? If he gives you no 0, then you know that something is forming, right? So then you can skip this whole step and just go straight to the ice table. But if 0 is given, I would suggest solving for Q first. Say it again. So that's if Q is greater than K, because then we would be past equilibrium and we need to take some ions out of solution to form the precipitate. I'm assuming he'll give you something like that on your practice exam.
So can you find X?
The concentrations that you have.
That would be your
Yep. And so then so you're going, right, you would have, right, you have these ions in solution. So you have, right, a number and you have a number. Q is less than K, or Q is greater than K, so you have to go towards reactants. So you're taking ions out of solution and forming precipitate. So you're saying minus X, and then you'll end up getting your number minus X and your number minus X. You then have KSP, so you can solve for the X that's needed. So then you can, once you find X, that's your solubility. So then you can find how much you need to subtract from those concentrations. Whatever you're subtracting from those concentrations turns into the concentration of your salt. So then that salt you can use in terms of concentration to provide volume, moles, and then therefore grams from molar mass. Similar, yes. Yep. Okay. And then last big one. Or anything else on question 12 before I move on? Okay. Almost done, I promise. We have silver chromate dissolves to form silver ions and chromate ions in solution. A student added this many grams of silver chromate to water such that the final volume was 775 milliliters. How many grams of silver chromate will remain dissolved or undissolved at equilibrium? So this kind of plays into it. Right, we're going more in the forward direction than reverse direction, but you could use this forward direction to see what you would have to do to solve for the reverse reaction. Okay, so the first thing I'm going to look at is the KSP. It's at the top. I'm not going to scroll for it. KSP will be equal to 9.0 times 10 to the negative 12. The next thing you're going to do is write out your KSP equation, which is silver chromate will form an equilibrium of 2 Ag plus and chromate ions. Questions so far? Okay, we're then going to solve an ice table. Your solubility for your salt for your solid can be neglected or as 1. So this gets neglected. We're given 0 and 0 because we're adding that salt that will eventually dissolve. We're trying to find out how much dissolves. What is our change for silver? 2x. What's our change for the chromate? X. So at equilibrium, we're going to have 2x and x. Not yet. When we plug into KSP now, KSP will be Ag plus squared, since we have a 2 as our coefficient, and then your chromate ion. So when you plug in your equilibrium values, this now turns into 2x squared times x equal to KSP, which is 9.0 times 10 to the negative 12.
So in this equation, the Ag2, that's the solid.
That's the solid. Yep, that's the precipitate.
And then it's being dissolved.
Yep, to form your ions. Yep. Okay, so now you can solve for x, right? You want to square 2, you also want to square x. So you end up with 4x cubed. So you can divide by 4, take the cube root, and you end up with x equaling 0.000131. This is the solubility of your chromate ion in solution. The solubility of silver would be twice this. What do we do from here? We need to know how many moles we have of the original grams of solution. So we know that we had 0.22 grams of silver chromate. We're given the molecular weight. What we're working in is molarity, right? This ends up being molarity here for the 0.000131. So we want to find the molarity of your silver chromate solid. So we're going to divide by 1 over 0.775 because that's how many total liters we have. And we end up with 0.000867 as our concentration. Well, either way you have to subtract your concentrations and then convert back to grams. Yep, we're gonna do that next. So this is how much we're starting with. We're gonna subtract out what we just found as our solubility, because some of that, right, will dissolve. So we'll have 0.000867 minus 0.000131, because that's the solubility, that's what's getting dissolved. We end up with 0.000736 molar that's left in solution as concentration of your silver chromate solid. We can then do the reverse of what we just did. So we'll multiply by 775 liters, because we have moles over liters. And then we'll multiply by 322 grams. And we'll end up with 0.189 grams.
I do not think that X is very.
I think you could also do that. I'm understanding the question now. I think you could also do that because, right, we converted to molarity and then converted back out of molarity. I think it should still work the same if you just kept it as grams.
If you were to do it that way, would you do the molecular weight CRO?
Nope, you would still do, because this is still the solubility of, so this is the solubility of silver chromate, so you can still use that. Your concentration of silver chromate will equal the solubility. The concentration of your silver will be twice the amount, because we have 2x at equilibrium.
So the X is the total amount of salt.
Yes, yep, the original salt. Yep.
Regardless, you don't have to take 2x.
Nope, because you already took that into account when you solved for KSP, or when you solved for X using KSP. Any other questions on KSP? Do you feel more comfortable with what the homework was giving and asking? Yes? Okay. If you would like to stay for the challenge question, by all means stay. If you're gonna leave, I'll give you a second to pack up your things. Just so we can fully go through it. I think I'm gonna sit down. Yeah.
So. The only thing, like, I understood everything, the only thing I'm just confused about is like, for this first one, you just used.
Yes.
The week after.
Yep.
The second one you used. Right, but like, I understand you got this one, but I just don't understand when you would just use the weak acid or the weak base formula, and then when you would use the one with water and then flip it.
Yep, so you just have the weak acid at the start, like you just have the weak acid or weak base at the start, because that's all that you have. You haven't added any extra strong acid or base, so it's only the dissociation of that acid or base. Okay. Then anytime you're adding or doing the titration, right, adding more titrant to your solution, now you have your equation of this, of, okay, some base is reacting with my weak acid, so now I'm forming this thing.
So say like if I, did you flip it?
Mhm.
Say I didn't flip it, say I just used this and I solved it like that, what would I do?
So,
Just to save time because.
yep, so I think you would have to use some sort of Ka. It's not exactly Ka because your acid is dissociating differently. Right, so your OH minus is now on the bottom, but your Ka is,
Would it be the inverse? Or no?
it's not the inverse Ka because right, you have HA and OH minus on the bottom here in this equilibrium and A minus on the top. Where you usually have H plus, A minus, and then
So
at the end of
just
them.
always. flip.
I would
Like,
just always
when
just
you, like, when
flip
we
it.
always have this equation, you just flip it every
Yeah.
single time.
Except for when you're in your buffering region, you just can use the Henderson-Hasselbalch equation. Anytime you're at the equivalence point or past it, use this equation.
Use that one.
Yep, flip it. Yep.
That makes sense. It's just a question. So what's the indicator that it's gonna be like a steep right here as opposed to like shorter?
So it's when you're in your buffering capacity, so
Yeah.
that's like that plus to minus
Yeah.
1 of your pKa.
Mm-hmm.
So anytime you're in that region where you have some acid and some base in your buffer, you're gonna be in that shallow region.
Right.
If you're at equivalence point, you're gonna have that spike.
But for like in between like weak acid, strong base, like between the different like types, I guess, you know how like one was like shorter, whereas one was like longer in his graphs?
Yeah.
What's the like?
I think that's just in terms of strong acid, strong base will
Yeah.
have like, right, really high pH and really low pH. And so your
Okay.
dramatic drop is gonna be, it has to go through 7 to get to your other like extreme.
So if it's weak, then that's gonna
Be a little bit shorter, yeah.
Shorter. Okay.
Yep.
Thank you. So this question, you see, oops. You said we can use Henderson has a bulk equation to solve for the equivalent.
Yep.
right?
Yep.
Well, we did that here for B.
We are
Um,
at the half equivalence point for B here,
Oh, okay.
not
right,
the
right.
equivalence point.
Okay, yes, all right, thank you.
Okay, so do you mind if I do the challenge question first, and then we can talk about this? Okay.
This.
Yep.
For this one, if it's a weak acid going into HCl,
Mhm.
wouldn't that just be false by itself because you need a base just over
Yes.
there?
Yep.
Okay.
Yep.
Okay.
Are we ready? We're still going strong, okay. So for our challenge question, we have 150 mils of 0.37 molar sodium cyanide was added to 437 mils of 0.25 molar acetic acid, and we want to know what is the final pH. Did anyone get the answer before I do it? Yeah, okay. So what you have to do here is you're looking at something that's completely dissociating and a weak acid, then forming another weak acid equilibrium. So you technically have like 3 equations you're looking at, and you have to take all into consideration. So the first thing you want to do is just break this up into the first 2 things that you're given. So we are first given sodium cyanide. So you have NaCN. What will this do? This will completely dissociate. Right? Sodium's in group 1, so we know that this will completely dissociate. This means that if we have 0.37 molar sodium cyanide, how much cyanide do we have in solution? We have 0.37 molar, because all of that initial concentration will go to your concentration of the cyanide ion. Right? It would also mean we have 0.37 molar of your sodium, but that doesn't matter. It's a spectator ion. We're not going to care about it. Next, we have your acetic acid. Weak acid will have an acid dissociation reaction to it. So we'll have HA partially dissociating to H plus and A minus. We have 0.25 molar of our acetic acid. How do we find how much H plus and H minus or H plus and A minus we have? Yep, right. We can just use our regular Ka formula. However, before we can use Ka in general, we have to take into account that these two things are being added. So we now have a change in concentration of what we have, right? We can assume that this will all, right? We said for sodium cyanide, all of this will go towards your concentration, but the concentration will change because we are adding volume from that weak acid that we're adding. So the first thing we want to do is we want to say we have 0.25 molar of your weak acid. We have 0.435 liters of this. And this gives us 0.10875 moles. To get back to that concentration in order to solve for Ka, we have to divide by our total volume. And our total volume here is 150 plus 435, which is 0.585 liters. So now it becomes HA, H plus, and A minus is 0.189 molar, right? So we see a reduction in that concentration, which makes sense because we're adding more volume. Okay. Now we can use Ka to find how much H plus ions we have in solution, right? Because the whole point of this is we're trying to find pH. So we need to know how much H plus is in solution. Same ice table that we are used to, right? This becomes I. We have 0 and 0. Change is still that minus X plus X plus X. Ka for this is 1.8 times 10 to the negative 5. And then you can use the assumption here. So this is X squared over 0.189. And X becomes a value I didn't write down, maybe. $1.8 times 1.84 times 10 to the negative 3. Okay, so this is how much concentration of H plus we have just for equilibrium, right? At if this was just isolated, this volume of your H plus. We can then find this new concentration for the cyanide. So we have 0.37 molar times 0.150. We get 0.0555 moles. Divide 0.585 liters, and we get cyanide concentration is equal to 0.0949 molar. Questions so far? So now we have cyanide ion concentration and H plus ion concentration. Cyanide, Cn minus, and H plus together will form HCN. What is HCN? What kind of acid? Weak acid. Strong acid or HCN is a weak acid. Okay, so technically we have H plus and Cn minus on our right. So we could flip this. So we have HCN is formed in the presence of Cn minus and H plus ions. Right now, our concentrations, right, initial, is 0.0949 and 1.84 times 10 to the negative 3. Which one's our limiting reagent? H plus, right? So all of the H plus would get used to form the HCN. But if H plus is getting used, what's going to happen to our acetic acid equilibrium? What does equilibrium concentration turn into if we use up all of our H plus? 0. Yep, it turns into 0. Right, so now it looks like the beginning where we just have a little bit less HA, right? A little bit less acetic acid, no H plus ions, and some A minus ions. So as you keep on taking this H plus out of solution and forming and using it up with that Cn minus, you're going to be shifting your acetic acid equilibrium more and more towards products. When will that stop? When the limiting reactant's done, which is when your Cn minus concentration and your H plus concentration are equal, and they will all form your HCN. Okay, so all of your Cn minus concentration will then be consumed after you've produced enough H plus ions to also equal that concentration. Does this make sense? Yeah. No, not yet, at least. Because we will have a situation where it's no longer initial of 0.049 in this, where it now becomes all of this gets used up to form your concentration of HCN. So now you're looking at a situation where you have HCN, Cn minus, and H plus, with an initial concentration of 0.949, 0, and 0, because you used up all of your cyanide ion concentration and all of your H plus ion concentration to form your HCN. Questions? Yep.
I just don't understand how, because that's a limiting one, so why wouldn't you just subtract 0.09 or 0949 minus 1.8?
Because, so you can do that, but you're going to get rid of H plus, which then throws off your equilibrium concentration or your equilibrium for the acetic acid, right? So acetic acid now says, I have no H plus, I'm not at equilibrium, let's dissociate some more. You use that up, it says, I'm not at equilibrium, let's dissociate some more.
Anytime you're doing from these, you can't get rid of the hydrogen.
Right.
Or the OH.
Yep. Yep, and it's basically, right, like if you're in an assembly line, the person, right, if I'm giving my calculator to the next person, this person's taking my calculator before I've even given it to them. So I have to keep on producing calculators in order to keep up with him still taking my calculator, right? That's like kind of how the reaction's happening. Does that make sense? Right, someone's taking things from me before I even give it to them. Okay. And that's because,
You can never have the acid or the base equilibrium.
right, your limiting reagent actually becomes your cyanide ion concentration. Because once that's all used up, now no more H plus is taking on a solution. Acetic acid's like, good to go. I've produced enough. We're at equilibrium still. Does that make sense? Mm-hmm. Mm-hmm. Yep. Yeah, you can definitely do it that way too. I tend to think of things as a flow chart. So I see it as this is happening, which is affecting this flow chart and flowing it that way. Yep. Okay, so understanding why we have just HCN right now, you're following-ish. But now looking at this equilibrium, are we at equilibrium? No, right? This weak acid is now saying, okay, I used up all of my cyanide, but now I need to produce some in order to be at equilibrium. So now we're going to do a Ka where we have change and a new equilibrium being formed. Should be easy. Ka for HCN is given to you at the top. So you can say that Ka is equal to x squared over 0.0949. Oh, this is minus x. Which is equal to 4.0 times 10 to negative 10. So you can assume that that negative x is negligible. So you get x, yep. I just messed up. I forgot a zero someplace, but it should be 0.0949, I believe. Yeah, it should be, it should be 0.0949. Yep. So x ends up turning into 6.161 times 10 times 10 to negative 6. Yep. Yes. So from your initial sodium cyanide, you're going to produce 0.0949 molarity of that. This becomes your limiting reagent because as you keep on using the H plus from the acetic acid, you will keep forming your HCN until you've used up all of your CN minus ions to produce that HCN. And so all of that concentration of your CN minus becomes your HCN concentration because it's a 1-to-1 ratio. Does that make sense? Does that help? Okay. Questions why X is 6.16. Okay. That puts H plus in solution. What does that now disrupt? Equilibrium of what? Not HCN. Because we just established equilibrium for HCN. What does it screw up? The original acetic acid concentration. So now HA, yep. We used up 0.0949 concentration of our H plus. That's 1-to-1 with that original acetic acid. So now our new initial concentration is 0.189 minus that 0.0949 that we used to produce all of that H plus, which is 0.0941. We now have 6.161 times 10 to negative 6 H plus. And how much A minus do we have? As we're producing H plus, that's being consumed to make HCN, what else are we producing? A minus. So all of that concentration of CN that we had is also the same concentration of the A minus we have. So this is 0.0949. Do we think we're at equilibrium? Nope. So we now need to do another ice table. You could solve for Q. We could find out that Q does not equal K. We need to produce more products. So now we have a situation where we have minus X plus X and plus X. Because we found this, because we had the H plus from our HCN. Yep. So we have 0.0941 minus X, 6.161 times 10 to the negative 6 plus X, and 0.0949 plus X. Yes. I subtracted 0.0949 from the 0.189 that we had originally because we had to use that much concentration in order to get to that much concentration of H plus in order to make the H plus react with this cyanide. How do I keep this straight? Very carefully. Questions on our equilibrium and our ice table? Probably so many, but not enough to, okay. I did the quadratic formula keeping the X's. I believe you could say that the 0.941 and the the 0.0941 minus X and the 0.0949 plus X, those are negligible and just keep the X from the H plus. I believe if you do that, you can solve this for just X that way, and you would get a proper answer that would give you a proper pH, because it's not going to be much of a difference that we have in solution. At the end of the day, you should get, and in whatever way you solve it, you should get an X that's about 0.000011796, something about that, right? So that's right, that's 1, 2, 3, 4 times 10 to the negative 5, pretty similar times 10 to the negative 6, and different from your times 10 to the negative 2. So it's pretty negligible. So then you can take your 6.161 times 10 to the negative 6 plus this value that you just found, and you get 0.000, and you get negative log of that value there, and you get pH equal to 4.75. And that's your challenge problem. What questions do we have? Again, probably so many. Does that kind of make sense what's happening? Right, you have a couple equilibriums working hand in hand, and so you have to take both of them into account while you're solving for pH. I don't think so. I think this is too long of a question for everyone to keep straight and get correct in order to ask. I hope not. For y'all's sake, I hope not. Yeah, he might give you another practice on like your practice exam. He might give you another type of challenge question. but I think he's just trying to get you to think about equilibrium this way. And see how things interplay, because we're not always going to have a strong acid weak base. A lot of the times we have this sort of situation in real life. This is all because it's a weak acid weak base. Yeah. Because your CN minus, right, is a conjugate base of a weak acid. So when you have a weak acid and a weak conjugate base, you now form more equilibriums.
Can we ask one?
Yeah.
So I know you told us something about that, but how do we know when we use Hasselbalch or whatever equation? Like, how do you know that these are before, like, for 9 and or wait, yeah, say 9 and or not, whatever we use.
Yeah, 9 and 10.
Yeah, we can use the hustle.
The Henderson-Hasselbalch. Yep. So whenever you're looking at this, if you have your weak acid, or if you have your weak component and then you have your strong component and you solve for the moles of those. If your weak component has more moles than your strong component, you will be before the equivalence point. Yes. Yes. Yep. Right. If you're going to have your weak thing and you titrate with a strong component, right. But if for some reason you have your strong component as your titrand, then yes, that also compares. But right, the whole point of a buffer and the whole point of titrating with a buffer is to mitigate your pHs, your change in pH. So 99 times out of 100, your titrate will be your strong component. Yep.
So your weak component has more yeah, than your strong component if the titrant.
Yep. So just in any case, no matter whether it's titrand, if your weak component has more moles than your strong component, you're before the equivalence point. If you have more strong than weak, you are past the equivalent point, and you can just use, nope, if you are past the equivalence point, you can just use what you have excess of, right? So if you have strong base that you're titrating with, you'll have excess OH minus in solution, and you can just solve POH.
Oh, because it's like, it's already giving you.
Yes.
In
Yep.
the ice table, it's giving you.
Yep, absolutely.
Oh, that's it. We have.
Yep. When your strong and weak are equal, that's when you have your equivalence point, and that's when you have to flip.
So that's the only time you have to flip.
Yep.
Is that equivalent?
Yep. Any other questions? If you have more weak component, more moles of weak component than moles of strong component, you're before the equivalence point and can use the Henderson-Hasselbalch equation. Yeah.
You know how we have like acid flow and then HA going to whatever. What's the one for base?
Yep, for base, it's going to be, I'll write it in blue here. It's your A minus, right? It's your base component plus H2O producing HA and OH minus. This is for your weak base. Right? Weak acid is HA. Technically has water too, right? But we know that H3O plus doesn't exist. It's just the H plus ion. Yep. So it's HA. H plus A minus. That's if you're just starting your titration and you just have a regular Ka problem, right? You just have that acid in solution. Yep. Yep, you don't have that extra titrate being added. You don't have that strong acid or strong base being added.
I think what's the relationship between
Yep, so at the half equivalence point, your concentration, right, molarity of your weak acid and weak conjugate base are equal. So your pH is equal to your pKa. Yeah, yep. Yep, so for strong base, we have strong base, we have, how do I want to write this? I'll give you an example. And strong acid, another example. Yep. No equilibrium, just a forward arrow. Yep.
Why, this is just a general question, why do we need to know if something's soluble or not?
Yeah, it just depends on the component you're using. For everyday life, like most things are going to be soluble. But I know like in lab, I actually work with a buffer where if we have a 1 molar solution, some of it will crystallize over time. But if we use a 0.5 molar solution, it stays in solution because that stuff will stay soluble. In that.
If you know it, yeah, I don't get like how, like for these problems, why you need to know something.
This is just for like your KSP stuff. And that's just to say if you mix two components, how much ions stay in solution and how much solid is left in solution.
So you don't technically need to know.
You'll need to know if it's soluble or not because you need to know if those ions, if they react, will form a solid or will just like bounce off of each other and stay as ions.
Oh.
Right, so you need to know that, right, sodium, potassium, lithium, all group 1 ions, those are always soluble. So no matter what happens, no matter what you put them in, no matter what they react with, they will stay soluble.
If it were to say in the problem, how many grams of sodium, whatever, will remain, it's gonna be nothing.
It'd be nothing because, like, how many of that will precipitate? It's nothing because that reacting with anything will always just completely dissolve.
Or like how much is remaining.
Yeah. Yep. Yep, so, they look very similar, but you have complete dissociation here with the forward arrow and equilibrium with the back and forth. There should be a solubility chart. Yeah. So a lot of times you'll see something like this. It's probably one in your textbook too, if you look up like solubility. But right, like nitrates, this C2H3O2, acetate, I think it is. Right, important exceptions means that whatever you react that with, it will always stay dissolved. There's no exceptions. Anything we react with will always stay dissolved. Chlorine, bromine, iodine, right, all that you see there, that's saying that everything will be soluble with it except silver, mercury, or lead. So if you see like lead chloride, that means that those, when they react, will form a precipitate. Just see how to like read that chart a little bit. And then same thing for the insoluble. We're saying, okay, those will always be insoluble. Those reacting with anything will form a precipitate, except if, right, your ammonium ions, that's will always stay soluble, or right, alkali metals, right, any of your group 1 stuff. And then, right, hydroxide, if you're looking at the chromium, strontium, barium, those are all calcium hydroxide is a strong base, completely dissociates, will stay soluble. Thank you.
For spectator ions, how do you know?
That has to do back with solubility.
Oh,
So if it's going to say soluble, that means that no matter what it bounces with, it just spectator doesn't work.
oh. And then also it basically tells, like at the top. The K,
Yep.
Would it be the KSP that tells us?
Yep, KSP would tell you if something, right, if it has a KSP, that means that it'll form a precipitate. Yeah. Yep, and if you, right, if you break up that KSP component that you have, right, if it says KSP of silver chloride, that means that silver and chloride in their starting materials, in their starting salts, will be soluble, and then they will be unsoluble when they switch their partners. Which means that the partners of that silver and chloride in the original will stay soluble too. Those are just spectator ions. Yep, KSP is your solubility product. You can look at the KSP, and if the KSP is not there, assume that it's soluble. KSP is telling you that it will not be soluble. Yeah. They're partially soluble salts.
Like the KSP, it has the equation up there that you know with the spectator.
Yep, because, right, if we look at your KSP, right, silver bromine or silver bromide, silver chloride, silver cyanide, that means that those will not be soluble, they'll form a solid. So if they came from, right, AgNO3 and HCN, right, these will dissociate into Ag plus and NO3 minus and H plus and CN minus. So H plus and HNO3, that's a bad example because that's actually going to form. Yeah. So if you did sodium cyanide, right, this would be Na plus. So sodium and nitrate will always stay soluble. They're just spectator ions. Yep, you could just ignore it. So like the net ionic equation would just be Ag plus and Cn minus, or sorry, yeah, Cn minus form AgCN. So your solubility is just the reverse of this, where it's AgCN is partially dissociating into Ag plus and Cn minus. And then so KSP is Ag plus times Cn minus. Because KSP is just showing your solubility product. So we use our reactant as the salt, and then your products are the ions.
Because you want to know
How much
each ion
is dissolving. Yep. Yep. Do the AgCN goes to Ag plus and Cn minus. Yep. Thank you. Good luck. So you could write any of these KSPs where it would be AgBr is an equilibrium of Ag plus and Br minus. It's insoluble. Yeah. Yep.
yeah, so those are all solid.
Yep, right. And they all say solid, 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 solid,
Yeah.
solid, solid, solid. Yep.
So it was PB in over 500 milliliters in 0.12.
molar,
Mhm.
KBR 200 milliliters of 0.14 molar.
Mhm.
And basically what he was getting at is that to find the limiting reactant, we had to use the ratio to then figure out what was actually less than. I don't know if I'm making any sense. So since this was 2BR,
Mhm.
then we to find the if we'd like test to see
Yes.
how much you would make
Yes, yep, so you want to know which one is,
in actuality.
yeah, producing less of that final component, and then that would be how much you inform, essentially.
You think they could show up?
Probably. I think that that's an okay question to ask.
So just to make sure I understand it, we use the, I guess, what this is for bromide. You know that bromide is 1 to 2 or
2 to 1.
2
Yep.
to 1. So then we would use the 0.28 moles and then 1/2 to cancel one out.
Mhm.
Then you get 0.14, and then you just compare these two together. You see that this is smaller, so then it's the
Yes.
limiting.
Yep. Yep.
Gotcha.
Yep.
Thanks.
It's just another type of limiting reaction question, pretty much. Yes.
Questions. So, my first question is, okay, so you know the problems like these, whenever we were solving, like this is like a weak acid and then this is strong base and stuff. So however, like we solved for it, because like the ones we solved for have been only like weak acid, strong base. So do you use the same like methods if it's strong?
Yep.
For
Exact same.
both strong?
No, if it's
So
just
that's what I
strong,
meant.
yeah, if it's just strong, then
Like
you just,
strong acid, strong base.
yep, then you're just looking at moles because your moles are going to be equal to each other. And so whatever you have less of, right, you'll have, like, it'll dissociate into H plus and OH minus. So whatever you have less of, you can solve for the pH or POH of that, and then solve for pH or POH directly from whatever is left, just through the concentration that you have.
Okay, so that's because like, so because.
Because you have
they're
no,
both Strong.
yep, they're
and
both
then-
strong.
But then the weak one was the challenge, the both weak was the challenge, so
Yes.
that's like, so then like, what if this was there'd never be a time where what if it's like a strong acid? Because-
Yep, you can do that. It's the exact same process
same
that way,
process.
where it's like, okay, you're gonna do the base dissociation, and then you have a buffering region, and then you have your equivalence plane.
And then, so for all of these, do we only, yes, like we solve the pH increase, but do we only care about the pH of the end, like whatever we're finding is like a common pH?
Unless it specifically tells you in the question defined for POH, yeah, usually pH.
And then, how does it more under- for question 20, I just like, is this like something that's like most likely wouldn't be shown up, or this is like something that's like, because like I have no clue like what this was.
Yeah, this is your KSP, and I think you just might need to review your KSP stuff a little bit more, in like what solubility product is. Because 12 and 13 are solubility products, and that's like at the end of the PowerPoint, and then probably what you like covered a little bit today.
Okay, so that like if I just like I don't know, go over the text, it should be
Yeah,
the-
textbook, and
yeah,
then if you look
sure.
at his slides with solubility product, he does a good job of like explaining that too.
Okay.
Just the breakdown of how you would solve one of those.
So using Q is only when you're doing like solubility patterns.
Q can be any equilibrium. Q is, you may or may not be at equilibrium, and you're trying to decide if you are or not. So you solve for Q the same way you solve for K, you're just questioning if you're at equilibrium.
Okay, I think I have to like brief up on that too, because like, I don't know, because like some problems like, we use Q and some problems we don't.
Yep, it's when you don't know if you're at equilibrium or not. So, right, if you know, right, how many moles you have of everything, you don't need to use, like, if you're doing a titration problem, you don't need to solve for Q, because you know that, okay, these will react and I'll produce this, so I can find pH this way. If you don't know if you're at equilibrium because you have some acid, some base in solution,
you've taken.
And then you can solve for Q and you can say, okay, I need to produce more products or I need to produce more
You have to
reactants.
go because
To like,
I
like,
had to read
cause
it.
like for some of them, it's like, okay, if it's at like 7, like the equivalents, or, yeah, the equivalents, right?
Oh,
And then if like the half equivalents, like, you can like identify this, but like, I don't know, I'm trying to figure out like how can you like identify that? Because like, I feel like there's just like so many steps and ways to get there, and I'm just like, not understanding.
Yeah,
Well, I mean, they took it, but that's.
and maybe that
They taken it like they're in college, yeah.
is something that like you, again, need to look at the notes for,
Yeah,
like
'cause-
his PowerPoint, because he will say like, okay, Q here is this, because, right, we have a 0 here, so we don't know, right? If your initial stuff in your ice table is something is a 0, then it's like, okay, are we at equilibrium? No, because if we solve for Q, then Q would be equal to 0. And when Q is less than K, because we have some sort of K value, we have to produce products. We have to produce something to make up for that 0.
And then that probably got 0. I like missed it right at the end when you explained like
Yep.
why it is 0.
So it's 0 because
It's like that millimeter. I think it was.
Yeah.
yeah, so this is the KSP, and right, this is because, so again, this has to deal with your solubility, so maybe after you read the notes, it'll be a little bit more clear. But you have certain values of ions in solution. So when you solve for Q, you don't know if you're at equilibrium or not. When we solve for Q, we get Q is less than K. So in order for K, so in order to get to equilibrium, we need to produce products. So if we're producing products, that means that we're not precipitating anything because we're actually dissolving more salt. So that's why nothing gets precipitated, because we're using some of that salt to dissolve more to get to equilibrium.
Okay, so whenever K is greater than Q, that's when you assume that it's 0, or no? Sorry, I don't think I'm like.
For this case, yes,
For
you
this,
can say that, yep.
Yeah.
I think I just have to like go over everything.
So you have, for you.
I already have my drawing.
I would suggest reading through the solubility notes again, and that might clear up a little bit of like 12 and 13. And if you have any questions, feel free to email me. I'm happy to answer them.
Thank you.
Yeah.
Yeah, it's just because I think I'm just like mixing up last units
Mhm.
and like in the beginning when we started learning, I was like, why are we doing this? This is like exactly like the last unit.
Yep.
And then now it's just like,
Yeah,
Like, I
and
don't-
at the end of the day, it all boils just down to equilibrium, right? Everything is always equilibrium. It's just the type of equilibrium you're working with.
so then this you said is like if you're doing with the bases.
Mhm.
Just, and then the other one is
Yep.
like acids.
Yep.
And I'll rack my brain before I leave. And then, okay, you said you flip it whenever, okay, I've done whenever you flipped it.
Mhm.
And then you said. I think I might be good.
Okay.
For some of them, like we're using this and some of them we're using this. Like why? Cause like for these, like you said, you can, for the last problems we did, I mean, that was the challenge, but like, we didn't, you said you can like null the
Yep,
X,
and that
okay.
just depends on how big your K value is. And that's just using the assumption rule. So if K is smaller than times 10 to the negative 5, right? So if you have like a value, an exponent of 10 to the negative 10, right? That's small enough where you can neglect the change in X.
Sorry, what's K? Because like I know we're doing like, there's like a million Ks.
Yep,
but, like,
and that's
just
just,
K,
that applies to any K, KA,
Oh, okay,
KB,
okay.
KW, KC,
Okay.
any K.
Okay. And then,
I was at it.
I was like.
I think I might be good.
Okay,
I don't think so, but I'll study.
Yeah. good luck.
Thank you.
Let me know if you have any questions. I still see people. Who's next?
Y'all can go. I have like a grading question.
I'm Nora.
Hi.
Hi, I am email person.
Okay,
Yes,
let me end my Zoom.
Yeah.